So production of a generator is very, very important because how importance we are giving in order to protect your distribution lines and in order to protect your transmission lines, the percentage of protection should be more in case of a generators. Am I correct? Because if the generator is not there, if you are not providing proper protection to a generator, then the power which it is developing or generating at the generator could not be able to do that one in an efficient manner. Therefore, the power is not going to get transferred to the transmission lines, and also the power can't be able to the load by using distribution lines. So from the starting point to the ending point, that is by using transmission lines and to the distribution lines and also to the load terminals, from the sending in terminals to the receiving in terminals, if the power need to be transferred in an efficient manner, if the efficiency of a power transfer should be more, then the production of a generator is very, very important. We need to provide a production of a generator properly. Okay. So as we already know, the generator contains with a stator and a rotor. So for that reason, we have divided the production of a generator as stator protection and a rotor protection. And also we have a miscellaneous protection, just like if there is an over voltage protection, if you want to compare, if you want to do some protection regarding the speed, then we are going to call it as over speed protection. Those all protections will come under miscellaneous protection. So right one. First one, stator protection. Stator protection. We have stator protection, rotor protection, and miscellaneous protection. So first one, stator protection. Under the stator protection, that is how we are going to provide a stator of a generator. That means especially how we are going to provide the protection to a stator windings against faults or against overheating or against interturn faults. So usually there will be three cases. The first case is if there is any fault, either that is a face-to-face fault or face-to-ground fault in case of stator windings. If a fault is taken place on a stator winding, either it is a face-to-face or face-to-ground fault, then we are going to call it as a stator fault. So in order to provide a protection, we are going to use some scheme, few schemes. We'll list out that one. And again, the second one is if there is an interturn fault. Interturn fault means if there is any circulating current flowing through the stator winding, then that will be also come under a fault. That is called as interturn fault. Okay. We need to provide a protection against interturn fault also. And the third one is if the stator is getting overheated. If the stator winding is overheated, then also we need to provide a protection against overheating of stator. That is called as protection against stator overheating. So these are the three different sections, the three different protection schemes we need to discuss under stator protection. The first one is we need to provide a protection against stator winding faults. Second one is we need to provide a protection against interturn faults. Third one is we need to provide a protection against stator overheating. These are the three cases or three disturbances where the stator winding of a generator is going to face. So the first one, you can write it as A. You can consider it as A. Percentage differential protection, right now. Percentage differential protection. Percentage differential protection. So this percentage differential protection will protect the generator against face-to-face or face-to-ground faults. Okay. And the next one, protection against, protection against stator interturn fault. Protection against stator interturn fault. So protection against stator interturn fault. Please switch off your mic. Who is the person? 21, I think. Protection against stator interturn fault. This is a fault related to the circulating currents flowing in the stator windings. And third one, stator overheating protection. Stator overheating protection. So these are the three types of protective schemes in order to protect the stator winding of generator. The first one, percentage differential protection, which it will provide a protection against face-to-face faults and face-to-ground faults. And next one is protection against a stator interturn fault. As the name suggests, it is going to provide a protection against the circulating currents or interturn faults. Next, providing the protection against overheating of stator windings. So these three will come under the stator protection. Second one, rotor protection. Rotor protection. Field ground fault protection. Field ground fault protection. Loss of excitation. Loss of excitation protection. Loss of excitation protection. Protection against rotor overheating. Rotor overheating. Not only stator, rotor will also get overheated. Protection against rotor overheating. So these three will come under the rotor protection. Field ground fault protection. And the next one is if there is any loss of excitation, then how we are going to protect the rotor windings. That is a loss of excitation protection and protection against rotor overheating. Third one, miscellaneous protection. Miscellaneous. If there is any over voltage protection, over speed protection, then we are going. These all will come under miscellaneous protection. That means it is not belong to either stator or either rotor. Over voltage protection. Over voltage protection. Over speed protection. Over speed protection. Protection against vibration. Not only these three, there will be a number of protections are there, miscellaneous protections. Protection against motoring, protection against vibration, overspeed protection, over voltage protection. So we'll discuss up to this point. So these all are the protective schemes under stator, rotor, and miscellaneous protection. So we need to discuss each and every type of protective scheme, and then after only we can able to complete the production of generators. Then we can move to production of transformers. Okay. So generator is not only a single machine. That means if you discuss the generator, it is going to contain voltage regulator. I think you already know AVR, automatic voltage regulator. It may also contain the governor. We are going to call it as a speed regulator. If this is a voltage regulator, governor is nothing but a speed regulator. Okay. It will also contain a prime mover. Okay. So there will be a combination of a prime mover. So the generator is not only depending on only its own parameters. It is going to depend on the governor. It is going to depend on the automatic voltage regulator. It is also going to depend on the steam turbine. This all will come under, based on this all things, we are going to provide the protection to this generator. So first we'll start discussing about the stator protection. So please, have you all listed out this one? Stator protection, percentage differential, protection against stator interturn fault, Stator overheating protection, again rotor protection, field ground fault protection, loss of excitation protection, protection against rotor overheating, miscellaneous protection, over voltage protection, overspeed protection, and protection against vibration. So now keep this heading as stator protection, and under that one percentage differential protection. Stator protection, under that one percentage differential protection. So we are going to use the same concept what we have used for the pilot protection. That means we are going to place two CTs. Why we are going to use the same concept of pilot protection means the generator is one unit. So this is also unit type of protection. If you are providing any protection to one unit, we are going to measure that one at the starting point and as well as at the ending point. That means if this is a generator, that means at the starting point and at also the ending point, we are going to measure the input quantities. Either you want to measure voltage, either you want to measure current, or either you want to measure the power flow, everything. So in order to measure that one, we are going to depend mainly on the current. So in order to measure that one, we are going to provide CTs at the starting point of a generator and CTs at the end point of a generator. So whatever the protective scheme we are going to see in case of protection of generators, we are going to use CTs at both sides of the generators. If we have a three-phase winding, therefore we are going to use three CTs at the starting point, and again three CTs at the ending point of the generator. I cannot able to call it as a primary or secondary because it is a generator. So keep this identity as a stator protection and percentage differential protection. Please all of you draw this diagram. Percentage differential protection. So this is the same concept, the circulating current protective scheme concept here also we are going to use. So the blue color winding, this indicates A, B, and C, nothing but stator windings, right? These three windings as stator windings of generator. Stator windings of generator. So for this stator winding of a generator, at the starting point, we are going to use three CTs. We are going to call these CTs as lower CTs. And at the ending point, we are going to use another CTs called as upper CTs. We can name it as upper CTs. We can name it as lower CTs. Because we have drawn diagram in a vertical way. So if you want to draw, if you're going to draw the diagram in horizontal way, then it is the sending end side CTs, and this will be the remote end side CTs or receiving end side CTs. So this is the amount of current flowing through the winding IA, in the phase B IB, in the phase C IC, and this is the circuit breaker placed. And in order to measure the current, we are placing CTs, lower CTs and upper CTs, and these are connected in a star manner. So if you see, this type of connection is a star connection because it is connected to a neutral or ground. Neutral will be available only in case of star connection, as we already know. So these 3 points have been connected to these 3 points of the lower CTs, and the phase C is connected to the respective phase C of this lower CT. See, this is connected. I don't know is my cursor is there. So this is connected again to this point of the CT, and this is connected again to the respective CT, respect to lower CT, and this is also the same. The upper CT phase is connected to this. And in between the connection of these CTs, we are going to use restraining coils or biased coils, also called as restraining coils. And we are also going to connect an operating coil with respect to this one. So this is an operating coil. The green color coil indicates an operating coil. So nothing but the combination. That means if a relay wants to operate, what happens? What usually the relay contains with an operating coil and a restraining coil. If the current is flowing through restraining coil as well as in operating coil, then only the relay is going to operate. If the current is not flowing in any one of these two coils, then the relay is not going to operate. We already know this concept of operation. So that means the relay contacts will close or the trip circuit will close if the current is flowing through the operating coil as well as through the restraining coil. All of you draw the diagram. So this is a diagram related to the percentage differential protection under normal conditions or external fault conditions. Under normal conditions or external fault conditions. The power is flowing from this point to this point, that is from lower CT point to upper CT point. Further, if you see the direction of the current in the stator winding, it is from lower point to upper point. For that reason, the direction is in like this. So the current is flowing like this, and again it is receiving by the CT. Again the current is flowing like this, and again the current is flowing like this. The direction of current is in this direction. For the CTs, it is in this direction. And also for this also, this will be in this direction. Apply the same concept. Why the current also is flowing in this direction? Because the fault is not internal fault, it is an external fault. In this case, the relay should not operate because the fault is not internally taking place, externally taking place. So if you come into the operation of this scheme, the current is flowing from in this direction and in this direction. Based on the direction only, we have given the polarities. See, this is the plus minus of this respective phase, plus minus, plus and minus. For this one, of course, plus minus, and plus minus. The current, if I talk, if we speak about this phase A only, the current is flowing like this, in this, and through the restraining coil, the current is going to travel, and again it is coming back to this point, this respect to CT, lower CT. So we have represented at the upper side as IA and at the lower side as IA dash. The current represented at the upper CT as IA and at the lower CT as IA dash of phase A. So the amount of current, that is IA, will be equal to IA dash in case of external fault conditions. That means there is no current is going to flow through this operating coil. If you see, the current direction is opposite. The current direction is opposite. The IA is in this direction, the IA dash is in this direction. If you add, because the magnitudes are same, if you add both, it will be in reverse. That means the summation of both the currents will be equal to 0. That means IA minus IA dash will be equal to 0. The same thing is I have shown in the operating coil. So the IA direction of current is like this. The IA dash direction of current is opposite. If you add these two currents, you will get 0. That means the amount of current flowing through the operating coil is 0. Similarly, in case of phase B and phase C, because the fault is taking place externally, this condition is called as normal condition or external fault condition. Therefore, in this condition, the relay is not going to operate because the current is not flowing through the operating coil. So percentage differential protection for external fault conditions or normal conditions. IA is equal to IA dash. IA minus IA dash is equal to 0. But what happens if an internal fault is taking place? The fault may be phase to ground, the fault may be phase to phase also. So this is the diagram related to differential protection for internal fault conditions. See, what we have done in this case is we are assuming that a fault, a phase to ground fault, a phase means here phase A to ground fault having took place on phase A, on the stator winding of phase A. So when the fault is taking place on only one phase with respect to ground, only that respective CT terminals of upper side will be get reversed. These upper CTs are there. So when a fault is taking place, that respective phase CT, upper CT, those terminals will be get reversed. So in the previous case, it is plus and minus, but this time it will be minus and plus. So therefore, the direction of current will be also in reverse. You see, the IB and IC direction is like this, IB dash and IC dash. But whereas only for phase A, the direction of current is in opposite direction. The current is moving like this. Here also the current is moving like this. That means the amount of current IA is like this and IA dash is also like this. This time, the IA, you will get IA dash is not equal to 0. If not, I can write it as IA minus IA dash is not equal to 0 because some amount of current is going to flow through this operating coil because of this reversal of current, reversal of polarities of upper CT. So IA dash is flowing like this, IA is also flowing like this. The summation of current is not equal to 0 in the operating coil. If some amount of current is flowing through the operating coil and the restraining coil also have some amount of current, therefore only this respective relay, this respective phase of relay is going to operate. Okay. The remaining relays are not going to operate. That means phase B and phase C relay is not going to operate. Only this relay will operate because the fault is on only phase A. For example, if the fault is on phase B, then this current, this terminals will not be get reversed. Only these respective terminals will be get reversed. Okay, only this respective terminals will be get reversed. So when these terminals are reversing, the current direction is also reversed. In the previous case, we got IA minus IA dash, but this time that IA dash is also getting minus. Therefore, you'll get IA minus of minus IA dash. Therefore, IA plus IA dash. This is not equal to 0 because previously it is 0 because of same magnitudes of current, but here it is getting added. In the previous case, it is deferred, therefore it is equal to 0, but this case it is added together and the amount of current is going to flow through the operating coil and also the restraining coil contains an amount that respective relay will operate. This is in case of phase to ground faults. You may have also you may get a doubt that, for example, if a fault is phase to phase, for example, if a fault is phase to phase, so this is a phase to phase fault. Then what happens? The circulating currents will flow through this one between B to A. Then the respect to remote end side CTs are going to reverse its terminals and only the B respective phase, that means A and B relays are going to operate but not C relay because the fault is on A and B. On this diagram, we need to draw the diagram for external fault conditions and also for internal fault conditions. Is differential protection for internal fault conditions. If not, you can mention this as figure P and the first one as figure A. So the diagram will be same. Only the difference is where you are going to locate a fault that respect to remote end CT terminal will be, polarities will be get reversed. So when the polarities is reversing, the current direction is also reversed. Therefore, the difference in between the currents is not equal to zero in this case. So this one we can consider as A. So while listing out the points, we'll mention as figure A and figure B. For that reason, I have written as A and B. Right on. The schematic diagram, figure A shows the schematic diagram of percentage differential protection, of percentage differential protection under normal and external fault conditions. Under normal and external fault conditions. So this type of protection scheme is used for a generator having rating more than 1 megawatt. So it is used for the protection of generators. It is used for the protection of generators above 1 megawatt. It protects the stator windings. It protects the stator windings of generator against faults. Against faults means we can mention as face-to-face faults and face-to-ground faults. Against face-to-face faults and face-to-face faults and face-to-ground faults. Face-to-ground faults. So it will provide 100% of protection of generator if the fault is face-to-face fault, but it will provide only 80 to 85% of protection if the fault is face-to-ground fault. Why? We will discuss the next ones. I repeat, if the fault is a face-to-face fault, then this protection scheme is 100% useful. If a fault is a face-to-ground fault, then this protection scheme will have an accuracy of 80 to 85% only. Why it is not providing 100% of protection in case of face-to-ground faults? I will tell you the point. So this is also called as biased protection. We also call it as a biased differential protection. Biased differential protection or longitudinal differential protection. Or longitudinal differential protection. These are the other names of this percentage differential protection. So what happens? As per figure A, in the operating coil, as shown in figure A, in the operating coil, the current sent by, we will write as, okay, the current sent by upper CT is cancelled by the current sent by lower CT. So both the magnitudes are same and both are in opposite direction. For that reason, we have mentioned as cancelled by lower CT. And relay does not operate because current is not there, and relay does not operate. For example, if the fault is taking place, then what happens? For an internal fault, as shown in figure P, as shown in figure P, for an internal fault, the polarity of the upper CT of respective phase of respect to, you can write it as respect to faulty phase, is reversed. Now what happens? Now the operating coil contains, the current is not going to get cancelled, but this time the current will be get added up. Now the operating coil, now the operating coil carries the sum of currents, sent by upper and lower CTs. You can mention it as IA plus IA dash also. Therefore, the relay operates. Are all of you following? First of all, have you understood the circuit diagram or schematic diagram explanation?
Yes,
Do you
sir.
have any doubt? Can I move to the circuit diagram again? I thought that it is the same concept what we have discussed in circulating scheme. For that reason, is there any doubts? You can ask me. In case of normal conditions and in case of internal fault conditions. Please go through the circuit diagram again, and if you have any doubts, you can ask me. In some textbooks, how the diagram will be in a horizontal manner, but not in vertical manner. Okay. In some textbooks, he is going to draw the diagram in horizontal manner. The same thing, if you are rotating this one in 90 degrees clockwise direction, you will get a horizontal manner. Okay. So it is named as a differential protection, as we already know that if there is any difference in the amount of current flowing in the operating coil, then the relay is going to operate. So therefore, the relay operates. And respect to circuit breaker and respect to circuit breaker, trips. And respect to circuit breaker trips. If it is phase A, that respective phase A will trip. Phase B, phase B will trip. Phase C, phase C will trip. If the circuit breaker is a three-phase breaker, for example, if the circuit breaker what we are providing in a generator, if it is a three-phase breaker, means if a fault is taking place on any one of the windings, if the relay is operating, means all the three phases will get open. Basically, we are going to use three-phase breakers only for the production of generators. So as I have already mentioned, the phase-to-phase faults will have 100% of protection. The percentage will be 100, but phase-to-ground faults will not have 100%. We will mention also that point. The percentage differential protection, the percentage differential protection. So the percentage differential protection does not respond to the external faults, and overloads. So don't worry about the syllabus. I think we are covering the syllabus based on the time given. Okay, so we are at half of the third unit is completed, and this will not take much time. Every production scheme will have its own circuit diagram and own respective points. So we'll complete that one. Then after, we'll move to the next unit. I think when we are discussing about the circuit breakers and fuses, that concept will be so much easier, and you already know those concepts, so we can speed up those concepts. External faults and overloads. It provides complete protection. It provides complete protection against face-to-face faults. Against face-to-face faults. It provides 80 to 85%. Provides 80 to 85% of protection against face-to-ground faults. Against face-to-ground faults, because the generator contains which depends on the method of neutral grounding. So we are discussing about a generator. If there is a generator, so, and usually the star point is a the stator is a star point of connection. So we are going to connect it grounding. Either it is a solidly grounded, or either it is isolated, or either it is a resistance grounded, or either it is a reactance grounded. So when we have discussed about the per unit system, we have indicated like this. So this is a generator, and we have indicated like this. So reactance grounded. And sometimes we have indicated like resistance grounded. Sometimes we have indicated like solidly grounded. Sometimes we have not indicating the isolated. So this protection, the percentage of differential protection will actually depending on this neutral grounding if a fault is a phase to ground fault. Because the fault is a ground type of fault, for that reason it is depending on this neutral ground. What type of neutral grounding? Either it is the reactance grounded, because the amount of current flowing will be different. If it is a reactance grounded, then the amount of current will be different. If it is solidly grounded, the amount of current flowing through the operating coil will be different. If it is a resistance grounded, the amount of current flowing through the operating coil will be different. Okay. So the amount of current flowing through the operating coil differ based on the method of neutral grounding. So for that reason, we are going to say that it is going 80 to 85% of protection is possible against phase to ground faults, which again depending on the method of neutral ground. So this is the reason why it is providing only 80 to 85%. And here, practically, another important point. We are saying that there is no amount of current is going to flow through the operating coil under normal and under external fault conditions. Okay, so this is the point. But practically, some amount of current is going to flow through the operating coil. Sometimes the relay may operate. Practically, some amount of current will flow through the operating coil. So in this case, what happens means the relay may operate. So for that reason, we could not be able to depend on other settings. We need to give the settings of the relay based on the location of that relay. Okay. So what is the amount of generator? How much is the rating of a generator? And how much amount of the current may flow in an operating coil? For example, if some amount of current is flowing in an operating coil. So this is a restraining coil and this is an operating coil. So some amount of current, practically if some amount of current is flowing under normal conditions, but the relay should not operate. That means we need to set the operating coil as some percentage. That means minimum this much amount of current should need to flow in order to make the relay to operate. Are you understanding the point? For example, some amount of current is flowing. This time taking an example of 10 amperes. Okay. So if 10 amperes current is flowing under normal conditions, the operating coil is carrying current. Actually, the relay should need to operate. But we are providing setting to this relay that the amount of current should be greater than 10 amperes or greater than 20 amperes. Then only the relay is going to operate. If you are not providing any setting, then the relay is going to operate if the current is 2 amperes, 3 amperes also. Okay. So that is nothing but settings. So we are going to give the setting for operating coil as well as a setting to the restraining coil. Right? The operating coil current what I okay. The operating coil current will not be zero, will not be zero under normal and external fault conditions. Under normal and external fault conditions in practical. So due to this current, the relay may operate. The relay may operate. But actually relay should not operate because it is normal and external fault conditions. So we need to provide the settings. So the settings are required for the relay to operate properly. To operate properly, to operate whenever it is required. What are the settings? The settings of restraining coil. The settings of restraining coil varies from 5% to 50% of full load current. 5% to 50% of full load current. Similarly, the settings of operating coil, the settings of operating coil varies from 10% to 100% of full load current. Of full load current. So these are the minimum settings of a restraining coil and an operating coil. Restraining coil, the minimum setting is 5%. Operating coil, the minimum setting is 10%. So that the relay will operate whenever the amount of current, the minimum amount of current, if the operating coil consists of either 10 amperes or 20 amperes, how much is, which it depends on the full load current. So this is about the percentage differential protection. So we have drawn the two schematic diagrams under normal conditions or external fault conditions and under internal fault conditions. And we have took example as a phase to ground fault, and with respect to remote end CT or upper CT, polarities have been reversed. We have discussed also the operation of these two schematic diagrams as well as the percentage differential protection. So in the next class, we'll discuss about the next protection, that is protection against stator interturn faults, nothing but due to the circulating currents. So if you see whatever the circuit diagram, the schematic diagram, it consists with CTs, restraining coil, and operating coils. That's it. These three components will be common in every diagram. We'll go for